Today we learn about different types of bridges. Before we go for continuity. And another important topic is DEF. I have sent this presentation to Bashita. Has he shared that with you? Oh, I think I have to send it. Bashita's number is 071 26 03 779. Good morning. Is that Bashita? Have you joined the lecture? Or you will not be able? Not yet. Right. We are starting. If you want, you can join now. Right. Okay. And can you send an email to others that we are starting now? Right. So basically, if you ask today, what is the cost of constructing an elevated highway? What is the value that you give? Satanayaka? Disanayaka? Ekanayaka? Would you like to give an answer? What is the cost that you generally record? Some say it can be about 7 to 8 billion rupees per kilometer. But my estimate is we can do it for about less than 5 billion per kilometer. Then why is this difference in cost? That is because of the way that we think about bridges and we design them. So can you all see the screen? The simplest possible bridge is a slab bridge up to 20 meters. Can you see it?
Yes, sir.
You can see it, right? Now, I'll use the camera also. I can explain many things. Come on. You can see the screen now. Can you see the screen? Can you see the screen, please? No? Not the screen, white sheet? You can see the white sheet. Okay, right. So basically, when you talk about bridges, a bridge will have an abutment. And the simplest bridge is bridge between two abutments. And what is the simplest bridge to construct? Just have a formwork, some supports, and place a slab bridge. A slab bridge. That is the simplest. Just create a slab. And this is generally we don't go for this, say about 8 to 10 meters. This can be very cheap. But in our tropical climatic conditions, our streams are very unpredictable. So doing a formwork like this is not that easy because there's plenty of water. So because of that reason, in Sri Lanka, we don't go for slab bridges often, except in dry zone. In dry zone, we get special type of bridges where we need the bridge, abutment, piers, and the bridge fairly wide. And there's only very little water during the dry zone, dry season, no water, little water. Then you can construct a slab bridge easily. And if you want, you can make it even continuous. Then you can go for 12 to 14 meters with a depth of about 0.8 to 0.9 meters. The rule is do not have anything greater than 1 meter, depth, greater than 1 meter, not economical. Why? What is the reason? 1 meter means 25 kilonewtons per meter square. And what is the live load? Live load is about 10 kilonewtons per meter square. So you can see dead load is 2.5 times live. What can you say? What is today is 12th, 11th, 2022. What can you say about it? Bridge is not economical. Why? So for a bridge to be economical, at least make sure the dead load is equal to live load or little more. Generally, what dominates the weight of the bridge? Dominated by deck. And then live loads also contribute. Weight of the bridge is dominated by deck, and then live loads, we get live loads in the range of 10 kilonewtons per meter squared. And did Dr. Bhaskaran use BS loads or Euro loads? What is the load used by Dr. Bhaskaran, please? BS 5400, part 2, 1978 or 2006. What is the load Dr. Bhaskaran used? Hello, Prasanna. Good morning. Can you answer? Can one student answer? What is the loading that Dr. Bhaskaran used? Tasanayaka, Meerani, Mahinda, Mohammed. What is the loading that you have already learned? Or you have not learned any loading so far? Can you answer, please?
Yes, sir.
What is the loading? You have not learned any loading, or you have learned loading?
We didn't use any loads.
You are not using loads. Okay. In that case, I'll give a brief description about the loads. Okay. But generally, you have to have some idea. Generally, you can have an idea that, you know, the loading is 10 kilonewtons per meter square. Just have this as a norm. For highway bridges, the load is about 10 kilonewtons per meter square. The highway loading. And how do you get this loading? You have trucks like this, 24 tons, about 6 meters long. One after the other. So what happens? You get a load of about 10 kilonewtons per meter square. Or we on the other hand, we can say it's 30 kilonewtons per meter per lane. Per lane, you get 30 kilonewtons per meter per lane. So that is the loading. And generally the lane is at least 3 meters wide. 30 divided by 3 is 10 kilonewtons per meter square. But if the lane is 3.5 meters wide, then the load is 30 divided by 3.5. Can be about 8.2 or something like that, approximately. Okay. So loading depends on the width of the road. That is all theory, all fashion. But the new theory is different. Eurocode loading is different, so don't worry too much about it. But generally, you should know what is highway loading. If somebody asks what is the magnitude of highway loading, you generally say it's about 10 kilonewtons per meter square. Right? So if you want to have an efficient bridge, what shall we do? We must go for some other material that is more efficient. What is the more efficient material? PT, Prestress. So in France, they constructed bridges like this, constructed by farm labor. During the time that they don't do farming, these people constructed bridges. So they are farmers, so they know how to do it. And the rainfall is very low in countries like France. The max rainfall is about 25 to 50 inches per year. What is the rainfall in dry zone of Sri Lanka? 50 to 75 inches. What is the rainfall in wet zone of Sri Lanka? 75 to 100 inches. So you can see whatever they do, we cannot do in Sri Lanka because our rainfall is very high. So they will go for some kind of formwork, or they will go for formwork like this. A truss. And then lay planks on the truss, cast it, and then they will cast it without this portion. This portion is not there. So they will place tendons like this and stretch the tendons and make it PT. So these are the type of thing you have learnt so far. You have learnt. Okay. So what is the sign convention used by Dr. Bhaskaran? Tension positive or compression positive?
Compression positive, sir.
Compression positive.
Okay. Compression positive. Right. So let's see what is PT. You have a beam. Then we apply a force at the center and we get P, the area is A, POA. Then we apply a UDL, say let's say 10 kilonewtons per meter squared, and that comes to say this width of the bridge is 1 meter. Then you get 10. So the maximum bending moment is WL squared over 8. And the span is say 12 meters. So you get 12 into WL squared, 10 into 12 squared divided by 8, 10 into 12 squared divided by 8. So that is the 180 kilonewton meters. And let's say the depth is 700. 700 is the depth. And width is 1 meter. So the self weight is 0.7 into 25. 0.7 into 25. What is that? 175 kilonewton per meter. 17.5 kilometers per meter. So the dead load moment is 17.5 into 12 squared divided by 8. 17.5 into 12 squared divided by 8. 315 kilonewton meters. So this is 12, 11, 2022, number 4. So the moment is this one. Okay. So we have a total moment of the dead is 315 plus 180. 315 plus 180. Total moment is 495 kilonewton meters. I'm not worrying about the factors of safety, so I'll just do it. And so we have bending moment. So we have MOI is equal to sigma y or sigma max is equal to M over Z. Z is 1/6 BD squared. Z is 1/6 breadth 1 into depth 0.7 squared. 0.7 squared divided by 6, 0.08166. Sigma max equal to MO is at 1/6 into 1 meter into 0.7 squared. 1/6. 95 divided by 0.08166. 495 divided by 0.08166. You get 6061 kilonewtons per meter squared, or 6.06 newtons per millimeter squared. Okay. So you get a stress, you get a moment, you get a stress. And what is the tensile stress allowed? In concrete is 0.36 square root of FCU, and FCU is say 40 megapascal. Then 40 square root of 40 multiplied by 0.36. That is 2.27. So what shall we do? We have to find a pre-stressing force. This POA plus we have a stress, this compression, this tension. Compression is positive, tension is negative. Compression. So the final answer shall be what? This has to be 2.27. Can you understand that? Because the maximum tension allowed is 2.27. So what is the maximum tension there? 2.27. Right? And then this is 6.06. And so what is POA? POA is equal to 6.06 minus 2.27. What is the value? 6.06 minus 2.27. 3.7. What is P then? P is equal to, what is the value? P. P is equal to 3.79 multiplied by 1000 multiplied by 700 divided by 1000. So that is 3.79 divided multiplied by 700. 2653 kilonewtons. Is it efficient? So axial pre-stress only. Is it efficient? Not very efficient. You need a massive pre-stress. So what shall we do? We shift it. We shift it. Not very efficient. So what shall we do? We take this section. We apply the pre-stress here. Is 350 with say 60 millimeter cover. We apply pre-stress. So the eccentricity becomes 290 millimeters. So that's what we do. So what will happen now? We have pre-stress. So what is this force? P here at an eccentricity E is equivalent to a pre-stress at the center plus a moment. Which direction? Apply this way, moment, equal to P times C. Now what happens? We get this stress POA plus this compression, positive. Then you get compression at the bottom, so positive. You get PEO is said. PEO is said. Now here you can see we have to measure this way and this way. So we need a sign convention. What is the sign convention? The sign convention that I use can be slightly different because this is the only sign convention that will work under any circumstance, like force hogging and sagging. So when you have a continuous beam, what happens? You need a sign convention that is applicable to sagging and hogging both. So I need a sign convention that is applicable to both situations. So how can I have a sign convention? So I say, measure this way positive. Therefore, the second fiber, bottom fiber is Z2 and Z2 is positive. Measure this way is negative. Z1 is negative. Because Y is, Z is I over Y is negative, Z1 is negative. Then we say compression at working positive. Compression at transfer positive. Okay. We say all that positive. Then we can write an equation. Under transfer conditions, we apply a P at an eccentricity. So we get P over A positive plus compression at bottom, tension at top, P over A over P over E times Z2, P over E times Z1, and it's a negative quantity. Because Z1 is negative, we can say P over Z1. P over Z1. Okay. So I'll get the light on because it's dark now. Raining here. Okay. Now we can write equations. P over A plus P E over Z2. If there is no dead load, should be, this is a compression failure, should be less than F compression at transfer. We can say P over A plus PE over Z1 should be greater than tension at transfer. So here we are saying -2 is greater than -3. Here we are saying 50 should be less than 60. Compression stress can be about 16 to 20, and the tensile stress will be about 2 to 3. Right? Whether you use British code or British, BS or Euro, these values change only slightly. Right. Do you know this? British code values are based on cube strength. Euro code values are based on cylinder strength. So when you are using equations for Euro code, you have to use which value? You have to use cylinder strength or cube strength. If you are using Euro code, you have to use cylinder strength. If you are using British code, you have to use cube strength. All the equations for BS codes are used based on cylinder strength. All the equations for Euro codes are based on cylinder strength. Are you aware of that? Yes. We learned it for concrete, so we should know it. Can you see the screen again? Can you see the screen, please? Sorry, I have not plugged in the computer, so computer became dead. Now what happens? We know when you are casting the beam like this, the slab like this, when you place the tendon and tension it, stretch it, what will happen? It will, this on the truss, what will happen? It can go like this. So that means MD also will start acting on it. Now we can write a new equation. POA plus is compression, so positive. Compression tension, PEO Z2, PEO Z1 plus, now you get this one, MD, this compression over Z1, MD over Z2, this tension is negative, so this is minus, this is a positive answer, but we know Z1 is negative, this is also negative. So we can write two new equations, POA plus PEO Z1 minus MDO Z1. Now this is a compression failure, sorry, this is a tension failure, should be greater than FT at transfer. POA plus PEO Z2 minus MDO Z2 should be greater than, this is a tension compression failure, should be less than compression at transfer. So in DS code, FTT is given as 0.36 square root of FCI at whatever the stress at transfer. But you generally we limit it to about 1 Newton per millimeter squared in class 1 structures, and in class 2 structures we go for 0.36 square root of FCI. Okay. There are class 3 structures where tension is allowed. So that's a different design philosophy altogether. So we will not stick with this one. So in class 1 structures, the tension allowed is 1 Newton per meter squared, whereas in class 2 structures, the tension allowed is 0.36 square root of FCI. And all our highway bridges are designed as class 2 structures. Okay. Is it clear? So if you are using DS code, 0.5 square root of FCI is compression at transfer. FCI means concrete strength transfer. So when you cast concrete, we generally stress in about 7 days. So 7 days strength has to be about 30 megapascal. If the final 28 days strength is about 40 megapascal. So if compression at transfer is about 15 megapascal, tension at transfer 0.36 1.97. Okay. This is a negative value, this is a positive value. Is that clear? Shantapriya, Rajapaksha, Kumari, Saranja, Disanayaka, is it clear? Ratnasiri,
Yes, sir.
clear. So what happens? Then what we do is, we have the bridge. Now we are applying, we are applying 10 kilonewtons per meter dead load. So the dead load moment, live load moment, we calculated at as 100. We calculated the value. The value is 180. We calculate the value as 180. So we have 180 kilonewton meters. That is the live load moment, ML. So what happens now? Now we have POA plus compression tension, PEO is at 2, PEO is at 1 plus, then we have MD over Z2 minus MD over Z1. These negative ones, these are positive answer, compression is negative, plus another one similar to that. And that is minus ML over Z2. Now we can write a new equation. What is the new equation? New equation is P over A plus P over Z1 plus minus MD over Z1 minus MD over ML over Z1. Now what is the failure at the top? At the top, what is the failure? Failure is compression. So it should be less than compression at working. And we get PO over A plus P over Z2 minus MD over Z2 minus ML over Z2 should be greater than tension at working. So now you can see we have 4 equations. If I write the 4 equations again, the equations will be like P over A plus PE over Z1 minus MD over Z2, Z1 should be greater than FTT. And I also get P over A plus PE over Z2 minus MD over Z2 to be less than FCT. Then I get this equation dealing with what is the page number? 8. So this is 9. 10. 11. POA Z1 Z1 and LO Z1 FCW P over A P over Z2 and D over Z2 and L over Z2 better than FTW. I think somebody has to record this. Is that right? I will record it.
Recording in progress.
Is there anybody recording it, please? Are you recording? Who is that? Jayasinghe? Good, good, good. I forgot to record it. It's good. You are allowed to record? Right, right. So I will give a recording rights to Atanayaka or Disanayaka. Is it okay? Disanayaka, can you record? Disanayaka, you can record, and Jayasinghe also can record. And Mehrani, can you record? So I allow recording rights to few. So please record whomever can. I'm also recording now onwards. Right. Now this is the most important part. Now we like to see, we take the first equation. Here we can see PEO is at 1. Z1 is negative, so this has to turn this way. Inequality has to turn because we are multiplied by a negative quantity. So you guess minus Z1 over A plus MD plus FTT Z1 over P. So this is equation number 1, 2, 3, 4. This is equation number 5. So we get E less than Z1 over A plus MD plus FTT Z1 over P. Equation number 5. Do you know what is equation number 6? You get a similar equation. You get E should be less than, E should be less than Z2 over A plus MD plus FCT Z2 over P. Number 6. Now here we need a small modification for equation number 3 and 4. Here we say it's RP. Do you know why RP? Because by the time the service occurs, there will be some losses. So we cannot say it's P, we have to call it RP. Then you get equation number 3, you get equation number. So you get E should be greater than Z1 over A plus MD plus ML plus FCW Z1 over RP. And the last equation you get E should be minus Z2 over A plus MD plus ML plus FTW Z2 over We get equations like that. Here, this will change to greater than, and we get the same pattern. Can you see? The sign convention results in similar equations. Once you write one equation, you can write all the other equations. So this is a very good sign convention. And what we do is, we draw Magnol diagram, marking Z1 over A here, that is positive, Z2 over A is negative. This is Y is equal to mx plus C or C plus mx. So this is 1 over P. And here you get, from Z1 you get two equations going that way. From Z2 you get two equations. And this is the feasibility region. That is the feasibility region. And within the feasibility region you get additional things saying that this depth has to be 290 millimeters. So only this part of the Magnol diagram can be. Can you see that? Can you understand it? This is called Magnol diagram, although it's called Magnol diagram. This is called Magnol diagram, or its actual name is Manuel diagram. Manuel is a Belgian researcher, the engineer. He invented this diagram. And when you write it in English, they write it in Magnol. So all the English people call him Magnol, but his name is Manuel. Did you know that? Have you drawn this diagram before? Jayanta? Indrajit? Ratnasiri?
Yes,
Dishanayaka? Yes. But you have drawn it E horizontal, P vertical. Is that right? Which
Yes,
direction you have got E? Vertical or horizontal?
Horizontal.
But I draw it vertical because we use prestress concrete this way. Eccentricity is measured downward from vertical. Is that right? So can you have a look at this? Look at the equations, 6 equations. This particular one is very important. Can you try and understand it? I'll give you a 10 minutes break. Try and understand this fully, because this is the basis for remaining part of the lecture. Okay. Now let's see how this evolves. First, we'll look at loads on the bridges. Can you hear me?
Yes, sir.
Can you see the screen? So basically, when you look at the loads, the bridges are supposed to carry moving loads, and then there are other types of loading that you have to consider. And then you get type B loading. And so we'll look at what is type A and type B loads. So this has to be 1 to HB is 1 ton, not 1 HA. So this is one of the loadings that was used earlier. And from this point onwards, this 30 refers to 24-ton trucks, one after the other. And what happens when the bridge is longer than 30 meters? Then if the bridge is very long, there's a possibility that cars also mix with trucks. So to allow for that, what is the way that is accounted for? A reduction in load is allowed. Reduction in load is allowed. And less than 30 meters, they have used a fixed load, 30 kilonewtons per meter. This is what was recommended in BS 5400 Part 2, 1978. But later, in 1990s, they opened this tunnel, the tunnel between England and Europe, where the trucks can be moved using the train. So in Europe, what happened was they allowed heavier trucks. Then they thought, okay, then England also, they thought they should allow higher loads on roads. And they allowed this type of loading. Here you can see for about 30 meters, you get about 30. But beyond that, you get a low value of 24 over 100 meters, and you go in a different line, and here also you get a higher value. Rather than a flat value somewhere here at 30, now the latest 2006 loading is much severe. And this 2006 loading is even severe than the Euro loads of today, very severe loading. But now they are using Euro loads. So we'll not worry too much about this curve because this is a very high loading. And we'll look at HB vehicle. HB vehicle is 4 wheels at 1 meter width, and the width of the vehicle is 3.5 meters. And the distance between this can be 6 meters, 11 meters, 16 meters, 21 meters, and 26 meters. So you can stretch the vehicle. Length of the vehicle can be stretched. And can somebody tell me why you can stretch the vehicle? So I'll stop share and I'll get the screen on. Now this is the reason. You have a bridge, short bridge, say about 40 meter length. To get the most severe effects, what do? You keep 2 HB axles which are 1.8 meters apart. This is the center line. of the loading. And you will make sure the center of the bridge, that is 20-meter line is equal distance. So this is 0.9 meters here, 0.45 meters. This is 4.45 meters. When you do this, you will get the maximum load on maximum bending moment due to these two. These two, you get the maximum moment here. When the one wheel is on one side, the other the resultant is on this side. So 6 meters behind, you get two more axles, 1.8 meters apart. So the total length of the vehicle is 6 meters and 1.8. Total is 9.6 meters. Total is 9.6 meters. Okay. So on the other hand, you have a continuous bridge. To place these two wheels here, we place the next two wheels very close to the center. What will happen? You get the maximum moment, maximum hogging moment over the support. So this will give the maximum sagging moment because the whole vehicle is on the bridge, and here you get sagging, maximum hogging moment. But here the distance between these two axes can be 26 meters or 21 meters or something like that. So they allow the HV vehicle to stretch. Here the HV vehicle can be 6 meters in the between axes, so it can go up to 26 meters. Now you can see the reason for that. Reason is by stretching the vehicle, sometimes you can get the maximum. And we are talking about 25 units for any bridge, 30 units for minor roads, 45 units for any other major road like the expressway is 45 units. But you won't believe that all our expressways are designed for 30 units. Our expressways are designed for 30 units and only Orugadawata flyover is designed for 45 units. Because RDA specified 30 units for Sri Lankan conditions. So you have to see whether it's reasonable. Just see some of our very heavy loads, 10-wheel Ashok Leyland, having 600 bags of cement, has a weight of 30 tons, plus this vehicle is 8 tons, 38 tons, over 10 meters. Over 10 meters, you get 38 tons. Okay? So when you are designing, you design for something like 30 kilonewtons per meter or 3 meters per 3 kilonewtons per meter, 3 tons per meter, 3 tons. So over 10 meters, you get 30 tons. Plus, you get 120 ton vehicle, 120 ton vehicle also. What is the reason for that? What is the reason for 120 ton vehicle? It's like this. Like this. So sometimes you have seen some vehicles like this, a number of wheels, and then you have axles, prime mover, and here you get 4 front wheels, and so the truck is like this, So here you get the trailer with all the load, with the load. And here you get 10 wheels, or eight wheels. It's like a sharp load, 120 kilonewtons. Plus 30 kilonewtons per lane. So if the lane is 3 meters, so this comes to a condition like 10 kilonewtons per meter plus 40 kilonewtons at the center. So that's how the load comes. Is that clear? Kumari, Saranja, Jayasinghe, is it clear? The HB load is 30 kilonewtons per meter. It has a knife edge load. So this is called a knife edge load. Knife edge load. Knife edge load. Knife edge load. And you get 30 kilonewtons per meter. What is that? That is the UDL. And then you have the knife edge load. And we have Ashok Leyland 30-ton load, but the chances are after that you might get pass and all that running. So to take account of that type of very heavy loads, we have the abnormal load. And this load is 1 ton per axle. Axle per unit. 1 ton per axle. 1 ton per axle. So if it is 25 tons, 25 units, the total weight of the truck is 100 kilonewtons over 9.6 meters. 30 units, 120 tons. "45 units, 180 tons over 9.6 meters. So if you design for this, can a Ashok Leyland truck cause any problem with just having a weight of about 38 tons over 10 meters? If your design satisfies this condition, what can you say about Ashok Leyland truck? Is it a big problem or not? Bashita? Jayasinghe? Radhasiri? What do you think?
Yes, sir.
Bridges are absolutely safe or not? They're absolutely safe. What do you think? Do you agree? Because it has 4 axles. And the length between these can be 6 meters, 11 meters, 16 meters, 21 meters, and 26 meters. And distance between these two is 1.8 meters. Okay? Then you will ask, what is the size of the wheel? Wheel sizes. Wheel will cause pressure of 1.1 newtons per millimeter square. So the wheel size changes based on the number of units. So if I stop this and start here, can you see the size is square, and based on the weight, you have to find the size of the wheel, size of the contact surface. Contact pressure is limited to 1.1 newtons per millimeter square or 1,100 kilonewtons per meter square. And you can see the road has to be fairly strong. surface, because if you take normal laterite soil, what is the strength? Maybe about 300, 200 megapascal, right? Sorry, 200 kilopascal. That is kilonewtons per meter square. Whereas the pressure that we allow by the vehicle is 1,100 kilonewtons per meter square. To take that pressure, the road has to be strong. Road has to be strong. Right? We are allowing a fairly high pressure on the road. So road should be capable of carrying that kind of load. So that's why you have to design the highway with using road note 31. Road note 31. Can you understand it? So the highway load is like that. But today, we have this new system where the lane width is limited to 3 meters, because earlier the lane width could change from 2.3 meters to something like 4 point something meters. Right? But now the lane width is limited to 3 meters. And what is the pressure that they use? 9 kilonewtons per meter squared. Can you remember I said 10 kilonewtons per meter squared as an approximate? And this is UDL, and then at the addition to that you get tandem loading and single axis tandem loading, and tandem loading here is 300 each, 200 each, 100 each, and here you get the load. These are the tandem axles and single axle, and each axle is 200 or 300. So here you get each axle as 200. So you have to apply loading like this. It's fairly complicated. So because of that, now they have written software like Midas Civil. You can generate all these load cases automatically. Otherwise, in my case, I generally look at the most critical and apply those critical ones and get the bending moment diagram. So people spend a lot of time finding the bending moment due to loading in highway loading earlier, but now all the software has automated it. Midas Civil can generate the envelope. So as SAP to CSI bridges also can generate it. But Midas Civil is more popular as among big engineers. Have you got the Midas license? Vashita, are you there or somebody else? You can apply for Midas license and use the full license. Is that clear? You can get the full license from Mr. Charaka. Jayasinghe. Have you got the license, Midas?
Yes, sir.
All right, good. So see whether you have to generate the bending moment envelope by using Midas automatically. I think it's possible to automate it. Once you ask it to try all the load cases and find the bending moment envelope, it will find it for you. I have not used it, but others said that it can be done. This is one of the features of Midas. You don't have to do it manually. You can ask the program to generate the bending moment envelope. See how to do that, right? Okay. And then HV vehicle is like this now. HV vehicle is like this. And it's a series of vehicles, a series of loads. 20 ton each, 20 ton, 20 ton. So you can see it's a fairly heavy load, HV load. It's like this. The abnormal vehicle can have a weight between 600 kilonewtons to 3,600 kilonewtons. So it can be of different weights, 2, 4, 6, 8, 9, 180, 108 tons, 300. So it can be 60 tons to 360 ton abnormal vehicle. So you have to select some loading for if you are using Euro loading, they have done the loading for all different types of scenarios. So you have to find some loading for Sri Lanka, and some studies have already been done by some of my research students, and we'll ask one of them to present their findings, right? And okay. Now, this is a very important statement by one of the best engineers in the world called Robert Benham. And if you go to internet and go to Google and go to pdfdrive.com. And then type under search type Robert Benham. Robert Benham. I have downloaded it earlier, but that hard disk crashed. But Benham in Bridges. Design of Prestress concrete bridges. It has 606 pages. So the book is available. That book is called Design of Prestress Concrete Bridges by Robert Benham, 14.63 megabytes. And Design of Prestress Concrete to Eurocode 2 is also there. There are so many Prestress Concrete books that you can download. If you go to PDF Drive, you can download those books. Design of Prestress Concrete by Robert Benham. It's a very good book. You can download and keep it for your reference. Okay? Is that clear? Is it clear? And
Yes,
just
sir.
read what he said. Concrete bridges designed to our courts of practice are at no risk of failure due to longitudinal actions under the specified traffic load. The search for excessive accuracy in the calculation of transverse distribution of moments due to live loads, for instance, is a waste of time. It's far more profitable to think carefully about stresses that can arise in the cast in situ bridge deck during construction due to temperature conditions, high initial pre-stress forces, settlement of foundations, and above all, heat of vibration. Can you see what the top engineer in England says? He used to be the best, one of the best that they have ever seen in England. And he came and taught in one of the courses, so I have used this lecture notes. So basically, we'll not go into great details of those, but I want to show you a few things. And there is a very cost-effective bridge, but I'll come to that later. But we look at this inverted T-type beams. I'll come back to that particular part of the lecture later, the slides later. So these are the type of first bridges people constructed using pre-stressed concrete, and you can see they are slab bridges. And Costain Domec is the company in England that manufactured all these bridges. And Bashit Iyer sent the paper by the engineer, the tailor who worked at Costain Domec. And then people learned that, you know, this bridge is too heavy, and for longer spans more than 14-15 meters, this is cheaper. So people started going for something above 17 meters. They started using these bridges. These are called MB bridges. And 16 to 29 meters they use. And this is the Y beam, the new one. The problem with this one is you can't do any maintenance. You can't do any inspection here. Nothing can be inspected from here. So they invented this one. Now here you can inspect the bridge, the deck. 160 in situ slab is what is required. And 160 is the minimum. Generally, you go for something like 200, 180 or 200. And so if you look at various bridges in Sri Lanka, you can see flyovers like this. Or the flyover like this. Do you know what is the cost of these two flyovers when originally built? 1,600 million, 800 million each. These are the flyovers, but you know those underwent very huge repairs later. And I think this can be the Dehiwala flyover, could be, or I don't know. And what is this one? Singapudi Bridge. Singapudi Bridge. Where is it? It's in Punari. What is special? This bridge is not meant for here. It is the Panadura flyover. Panadura flyover finally ended up as Singapudi Bridge. Singapudi Bridge is not meant to be there because it is a bridge not meant for coastal situations. So I'm not very sure whether they have taken any special precautions when this bridge finally ended up there. What is this one? This is Orugodawata flyover that I designed in 2006. And cost, these again 4-lane, longest in Sri Lanka, 560 meters long. The flyover alone is 330 meters. With the embankments is 560 meters. And do you know the cost? Same era, 520 million. So this is 2,600 million. Shorter, 300 meters. These 560 meters, 500 million. So cost can vary a lot depending on who the politician who is promoting it. This was not promoted by anybody, so it was a government project, RDA project, by a Chinese contractor. The original RDA design was like this. The original RDA design was like this. It had only 10 numbers of 30-meter spans. And the bridge was closely resembled the Mattakulia bridge. Do you know the story of Mattakulia bridge? Yes or no? So 10 beams like this, and then connected like this, and then you get so what was the problem? There are pipelines all over the place. There are pipelines. So the Chinese contractor proposed a bit like this on 2 piles, on 4 piles. And instead of all these, he proposed 4 beams. So the Chinese contractor's solution was do you know these cantilevers, 5.5 meters? You know what is the size of this one? 4 meters. This is a bridge. So I designed it in 2006. And then it was not accepted by RDA. So we waited until Dr. Asoka De Silva retires. And the day he retired, this was accepted. So it was nothing wrong with the design, it was something wrong with the perception. So this was much cheaper. So the contractor gave a discount. So under FIDIC conditions, do you know what is the rule? Under FIDIC conditions, do you know the rule? Under FIDIC conditions, do you know the rule? FIDIC. To do value engineering, you have a project for 600 million. Contractor gets it for 600 million. And then contractor hires somebody who can give a design for 400 million. So the contractor comes with the design engineer who will do it for 400 million. Then the client accepts it, 400 million solution. Then for client to accept it, client is not getting 200 million reduction, 50% for client, 50% for contractor. Okay. So client will get the project done, initially 600 million. Now the contractor will reduce it by 200 million. So the client's cost is 500 million. Contractor get 100 million profit. Out of that 100 million, contractor will keep 80 million. What will happen on the remaining 20 million? To the design engineer, value engineering design, Value engineering design against the remaining 20 million. Is that clear? So that is a FIDIC rule. So value engineer has done the design at 10% of the saving. And we also do value engineering at 10% of the saving. And that is 12, 11, 20, 22, and 60. This is 70. Okay. So I think the contractor gave some, gave some 40 million discount, and finally the original estimate is for 750 million for this project. So out of 750 million, 260 million was pipe diversion. Contractor was given as 490 million. So finally the contractor did the project for about 450 million, and RD said they have to give a discount to accept the design, and the pipe diversion cost was 60 million. The total was about 510 million, and the original estimate was 750 million. So more than, say, it says 1/3 cost saving due to a good design. Now today the same design is adopted in outer circular road. And it has two beams, so I will just draw a slightly different version of that. Two box girders like this, large box girders, and each total width is 21 meters, whereas the bridge I design has a width of 17.6 meters. So this is more advanced design because it's for the continuous structure. So it is monolithic, so you get this constructed as monolithic system here. So pier and all constructed like that. No pier capping beam. Instead of pier capping beam, the pier, they have a solid pier like this. Pier capping beam is like this. And then the other beams will come like that. Two beams. So this is the port access road. It's, I think, 26 billion rupee project. .2 kilometers long, elevated. So you can see they are doing a 6-lane highway, 5.2 kilometers of elevated, at around 5 billion rupees per kilometer. In today's terms, after all these price escalations, now the cost can be slightly more. So just look at this and try to understand the philosophy. And how do you achieve this? You go for Prestress. Otherwise, 5.5 cantilevers are not possible with RC. So this is the first bridge with force tension pier capping beam in Sri Lanka. And this is the port access may be the second one. I designed this bridge with PT capping beam in 2006. So port access road is an elevated expressway, but this is a flyover. Orgudavat is a flyover. So the longest flyover in Sri Lanka as well as the tallest bridge. All I had some involvement. So what you learn is from a person who has actually done proper good designs. So whatever you learn will have great value when it comes to practicing. So these are good. These Mattakuli. Do you know the story of Mattakuli bridge? The minister was Pausi, and he was the highway minister. So these are Chinese design, I think. It's a bit turnkey contract. Yes. About 10 deals like this. And then a wide here on piles. And the contract price was 210 million. And engineer Nimal Chandasiri. The project director. And he completed the project for 200 million. Across the same bridge, Japan gave a grant, a free bridge, which had a box girder. Yeah, box girder for large box girder. So this was free. Then they had another box girder. The contract, 760 million. So across the same river, when Japanese guys construct a bridge, it costs 760 million. When the Chinese construct the same bridge, it costs 200 million. So you can see in Sri Lanka, bridge prices can vary hugely. When the minister brings steel flyovers over 300 meters, flyover cost is 800 million. When the same countries 560 meters, 4-lane, these 2-lane. Sri Lankan engineers design 500 million. 500 million. 4 lanes. Huge difference. So when this Orugodata flyover was opened, by whom? Then President Mahinda Rajapaksa on November 2009, just before the elections, 2010 January elections, he said, all future designs, bridges by Sri Lanka. So for Matara, who designed the bridges? Sri Lankans. Then Central Highway, phase 1. Who designed the bridges? Sri Lankans. Phase 2, again by Sri Lankans. And I think outer circle also So designs came from Sri Lanka. So because of this, now Chinese contractors know Sri Lankans are fluent in BS codes, Euro codes, and all that. And when they get contracts in Africa, so we have India, Sri Lanka, Arab, Africa. They hire Sri Lankan engineers to do the designs. Why? The Chinese don't know English, BS codes, they are not familiar. So they like Sri Lankan engineers doing the designs. So that is the situation. They like our engineers doing the designs. So that is a new market that has opened up. In the recent times. Did you know this? That such opportunities are available in this country, where the designs are now done in Sri Lanka for most of the African projects by Chinese contractors. Bashita or somebody else? Indrajit? Or Amarasena? Attanayaka? Disanayaka? Do you know that? It's happening. Like that. Anybody there? Jayasinghe, Milinda, Nelundenia, Rajapaksha, Mirani? Are you all there or you are just vanished? Satyasiri, are you there?
Yeah, yes, yes.
Right, okay. So we'll go back. So this is Mattakkuliya bridge. So RD adopted the Mattakkuliya bridge for Orugadatta, then the Chinese contractor came up with the new design where only 4 beams were there instead of 10 beams. What is this bridge? Periyamuttuvaran bridge. Periyamuttuvaran. I again designed this bridge for Maga Engineering in 2009. And do you know how much time I spent to design this bridge? I used the spreadsheet that I developed for Urugadatta flyover. So I completed the design in 3 hours and gave all the details to Mr. Nuwan Senak of Maga Engineering, the chief structural engineer. He designed the substructure. You can see only 2 piles, and we use 4 piles, 4 or 6 piles for the abutments, but only 2 piles, 2 piles each. 2 1.2 diameter piles. It's a very fast constructed structure across estuary and the shallow water, so the water was not a major problem for construction. The coastal structure, Prestress concrete. Maga did the construction in about 4 months. 4 months, and it's on A32 highway. A32, no, sorry, it's on A4 highway, not A15. A4 highway. Oh, no, A32. A32 highway. That's A15. I think A32. Just one moment. What is the highway beyond yes, A15. Yes, that's correct. A4 comes up to A4 is the highway up to Eravur or Kattankudi. Kattankudi is just above Batiklo. Kattankudi is up to Batiklo. From Batiklo onwards, the highway is A15. Kattankudi is the place the highway A4 comes from. A4 comes. Just one moment. A4 is the highway from Colombo, Ratnapura, Batiklo. A4 is Ratnapura, Batiklo. Sorry, Ratnapura, Palmadulla, Balangoda, Aputale, Velavaya, Buttala, Monragala, Simalandu, Potuvil, Akkarepattu, Samanture, Kattankudi. That is the highway, longest highway in Sri Lanka. It is called A4. A4 highway. A4 highway. And A5 is also very long. A5. A5 is also very long highway, but longest is A4 highway. A5 starts at Nuvareli, it comes to Badulla, then it goes up to Bibile, Padiyatalawa, Mahoya, and Eravu. Goes up to Eravu. But then A15 starts, this is correct, A15 starts. A15 highway has so many bridges, and A22 is Mana Jaffna highway, and that's where that bridge was constructed. I said Panadura flyover, that's on that highway, and this is on A15 highway. This is correct. And A15 highway also has 5 bridges up to Trincomalee. From Batiklo up to Trincomalee, it has 5 bridges. And 2 bridges are 150 meters, 2 bridges, one bridge is about 175 meters, the other one is 125 meters. And the Verugal bridge is 50 meters, 70 meters, 75 meters. So, and also then you get Kinya bridge. There are so many bridges on that line because of Mahaveli River meeting Mahaveli bridge, meeting the eastern coast. There are so many bridges on A15 highway, and so there are so many bridges on that one. And if you look at the map, you can see there are so many bridges on that particular highway, A15 highway. And this A15 is called Trincomalee Highway. Yes, it's called Trincomalee Highway. And then you can see from Trincomalee, you don't get much good road up to Jaffna. But if you have a good road up to Elephant Pass, then Trincomalee to Jaffna would take only little time. Now it takes a lot of time. Right. Okay. So, so this A15 highway bridge and the same bridge, and there's another second bridge also constructed, 3 span 75 meters, again by Marga. So these are the photos of that particular bridge, eye girders. They can be used up to 45 meters. And so loads acting on a highway can be different, and I will not. Okay. This Orugodawatta box girder after pre-stressing. And this is they use some rubber void formers for the ducts. This is the end block design with spiral reinforcement, and this pre-stressing and this you can see the bridges be lifted up. They are being kept for launching. So the launching of bridges on top of the beams that have already been launched. This is the bridge, the shear keys. There's a diaphragm. These are what will happen if you use plate girders, and how to perform structural analysis by using relays. Using relays. I'll show you how to create the relays. I'll come back to those later. And then how to create continuous bridges by using PT bridges. There are different types of joints like this. There are different types of joints, and we'll come to that later. And abutments like this on rock for Hammankota flyover. These Orugodawatta flyover access roads by using what you call cement reinforced earth construction. So these are the reinforced earth panels with these are the strips used for reinforced earth. Do you know what is reinforced earth? Have you heard about reinforced earth? If you have an abutment with some panels like this is the failure surface. So all this will be in tension. So what we do is we take strips, we anchor the strips in the compression zone. So these are in tension. So these can be metal, plastic, cotton, metal strips. So we bury them, and anchor it like that, so that these panels we have sufficient strength. So the soil holding the abutment. This reinforced earth very cheap, much cheaper than constructing an abutment. So reinforced earth was used in this particular bridge. And then in bridges you get running slabs. A running slab is something like this. So we have the abutment. You have a slab like this, resting on soil. So when the soil settles, you can enter the bridge without a jerk. So this is called a running slab. So running slabs can be used in bridges. It's just a slab that we allow it to settle with the soil so that you can avoid the sport settling before the abutment. So this is a running slab. So this is the kind of forces that will act on an abutment. And this is Hammantota. There's a flyover. We really don't know why flyovers are needed in Hammantota, but there's a flyover. Miriji below somewhere. That was on rock directly. And this is the Oruvadatta. You can see 4 piles, the pile reinforcement anchored into there. So these pouring of piles. So, okay, this is what happens. What is this? This is called delayed detrengite formation. Shall we take a break and then talk more about it? Bashita, Jakodi, Indrajit, Disanayaka, Atanayaka. Huh? Shall we take a break and then talk about it? DEF, delayed detrengite formation. Do you know how it occurs? Any answer? What are the constituent materials of cement? 50 years ago. Now, C3S, C2S, C3A, C4 aluminoferrites, 50%, 25%, A2, 10%, rest is impurity. This is an impurity. Now, 65 to 70%, 5 to 10%, 8 to 10%. So what happens? 50 years ago, this is the stem development curve, gradual. $28 days, 1 lot, 2/3 in 7 days. What happens now? Goes flat. Goes flat. Why? In 7 days, you get 28 days. Why? Lot of C3S. C3S is effective from 1 day to 14 days. After that, very little reaction. So you get very high strength early. You get very high strength early. Right. So what happens? These are exothermic reactions. So heat how hydration goes up. And if this temperature is more than 70 degrees, what happens? C3A plus H2O, you get a combination and it breaks back, comes back. So you have hardened concrete, it has C3A, and if moisture comes, the reaction starts later. What is the problem? Volume is high. Volume is high. So this will start putting pressure on all directions. So if there's not enough steel, what happens? Cracks. The designs were by CCB, approved by British consultants. So what happened? Approved by British consultants, did not have enough steel, so it cracked. So what we have done is we have developed curves. These curves will allow you to select for 0% fly ash, 5%, 10%, 15%, 20%, 25% fly ash. We have developed the curves so you can easily today decide which cement content to be used. So this happens because not enough steel and too much temperature. And how do you reduce the temperature? By having steel tubes and circulating water. And there's software to determine the total maximum temperature. And we calibrated that software and developed these curves. So this 0% curve, only fly ash, no fly ash, only cement. And you can see if it is only cement, very thick sections, only 275 curve is okay. So if the cement content is less than 275, you can cast any thickness without worrying about DA. But these days it's cheaper to use fly ash, so you go for 15% or 25%, and then you can see for 1,000 millimeter thickness, you can even use 375 cement, and for 2,500 meter section, you can use up to 325 cement plus fly ash. Cement content can be 300, where 25% is fly ash. 25% is fly ash. And here cement content is 400, where 25% is fly ash. So by doing that, you can get, you can control the temperature. And piers are like that. And these are the piers of Orugodota flyover with 16 meter pier capping beam, it's supported on 4 meter. The cantilever is 5.5 meters. And you can see the precession ducts, curved ducts and the straight ducts. Then right, so we'll go back to the presentation. And I'm now interested in teaching you about this particular type of construction where we get M-beams. And you can see the beam. And on top of this beam, you get another concrete. Like this. Now, how do you write the equations for this situation? So we have a beam. So this is what we are interested in now. So we have a beam 1 meter wide, let's say 1 meter wide. of this right. The top step can be about to is initially like this. Later cast. Okay. So centroid of this section is y1, y2, z2, y1, z1, and for this section we get I dash, so we get z2 dash, not from here, here. Hello, good morning. I dash and y2 dash. So now we have to see what are the equations that are applicable. So if you look at the equations, POA has compression, PE over Z1, Z2 plus PE over, sorry, MD1 over Z2 plus this way plus compression above, tension below, MD2 over Z2 plus M live over Z2 dash. So let's see what happens. First we cast the beam. When we cast the beam and cut the tendons, these three equations apply. So this is MD1. Then we place the beams. We cast the top. This is MD2. Then we apply live load. This is MA. So we get a situation like this. So if I write the equations, this is 12, 11, 22, 23. So if I write the equations, this is P over A plus P over Z1 minus MD1 over Z1 should be less than FT at transfer. Should be greater than POA plus PE over Z2 minus MD over Z1, Z2 should be less than compression at transfer. So those two equations will not vary. Why? This is the same situation as before. Then we can have an intermediate situation which says POA plus P over Z2 plus MD minus MD1 over Z1 minus MD2 over Z1 shall be less than F compression at working P over A plus P over Z1 Z2 minus MD1 over Z2 minus MD2 over Z2 should be greater than FT at working. But these two equations are generally not governing, because we are talking about only the weight of this concrete and it cannot be a governing condition. It's not a governing condition. Then we have another situation, P over A plus P over Z1 minus MD1 over Z1 minus MD2 over Z1 minus ML over Z1 should be less than compression at working P over A plus P over Z2 minus MD over Z2 minus MD2 over Z2 minus ML over Z2 should be less than, should be greater than tension at working. These two are governing, but this is Z2, Z1 dash and Z2 dash. And Z1 dash is up to this side. Z1 dash is up to this side. This is Z1 dash, which is not governing. Again, not generally not governing. Will not govern very much. So the governing equation will be this one. So what we do is we write the equation E, which is greater than minus Z2 over A plus FTW Z2 plus MD1 plus MD2 plus ML divided by RP. So this will be the equation number 6. Equation number 8. So if I write the four equations will be E less than Z1 over A plus MD1 plus Z1 times FTT over P. This is equation number 5. You can compare it with the earlier equation. Same equation. The second equation is Z2 over A plus MD Z2 F CT or P. Number 6. Then the seventh equation is E should be greater than Z1 over A plus MD1 plus MD2 plus MD2 ML over Z1 dash multiplied by Z1 plus Z1 times FCW. Same as this one. Only this ML term is different. Same equation RP, not a governing. E should be greater than minus Z2 over A plus MD1 plus MD2 plus ML over Z2 dash times Z2 plus Z2 times F TW over RP. So when you are doing composite construction, again we have four equations. E 1 over P minus Z1 over A minus Z2 over A, and you can draw a Magnell diagram and then impose the maximum extensity condition and get a feasible ring. Again, it's possible for composite construction. Is that clear? Indrajit, Disanayaka, Attanayaka, Amarasena, Nuwan, Giriagama. How is it? Is it clear? Can you understand it? Clear or not? I have just rearranged the equations, huh? I just rearrange the equations. This did Dr. Bhaskaran taught you this particular part? He covered composite construction. Did he? So he has already taught this, huh? Okay. So with all this knowledge, now I'm going for the continuous construction. Continuous beam. Beam is continuous. Dead load, deadlock. What is shape? Can you get a dead load envelope like this? Difficult. Why? We can't construct the structure like this at once. Generally, what we do is we construct the structure like this in stages. First stage, this one. Second stage, this one. Third stage, this one. Fourth stage, and so on. So what are the bending moment diagrams? This. So monolithic at once, we get a bending moment diagram like this. Actual, we get a bending moment diagram like this. So this is actual, addition of all three. This is monolithic. But what actually happens is this is called locked in stresses, locked in moment. Locked in moment due to creep deformations. After 50 years, you will find now this has moved closer to this. Say about 50 to 60% of this locked in moment is lost. Although you get a locked in moment can be lost with time. Can you understand it? We can't construct a bridge at once. We have to construct in stages. So when you construct the bridge in stages, if you construct it at once, you get this as the bending moment diagram for the dead load moment. When you construct in stages, you get each stage you will get a bending moment diagram. Then you have to add those three bending moment diagrams. Then only you will get the final bending moment diagram. So this will be the purple color is the actual Monolithic is blue color. This is monolithic. This is actual. But again, you can't use actual for calculations because actual is going to change with time due to creep deformations. This is called locked-in moment, and locked-in moments are lost with time. So you can't use this, you can't use this. So you generally, in continuous construction, this is the actual bending moment diagram. This is the monolithic. This is actual. This is monolithic. This is the actual. So dead load moment diagram is an envelope. Why? With time it will change this way. So locked in moments disappear with time. Disappear with time. So we use an envelope. But for continuous, I will consider it as a moment diagram. For to understand it easily, let's say bending moment diagram is like that. There's a live load diagram. Let's take 3 spans. You can have the whole bridge loaded, ML. Then you can have 2 spans loaded. Then you can have 1 span loaded. So you get sagging over the support. And you also can get hogging over support. So what is the shape of the bending moment envelope for a continuous structure? We know spans should be like this. Supports should be like this. And then you can get something like this. Something going like that. Something going like that. So this is the shape of the live load moment. So it can be either sagging or hogging. So when you cast the beam, it will go like this, transfer. Then when you have the live load negative moment, it can go this way, MA, or it can go this way, MB. So it can go either direction. So this is the maximum moment. This is the minimum moment. So this is MA, MB, this is MA. Minimum moment is MA, maximum moment is MB. So what can you say about the bending moment envelope for a continuous structure? Let's say live load is considered as a diagram, although it's an envelope. When you superimpose, the minimum moment will give something like this. Maximum moment will give something like this. So this called MA, MB moment, this called MA moment. What is a transfer? Transfer is in between. So transfer is not governing, empty, not governing. Empty is not governing. Why? Transfer is in between because these moments can be big, much bigger than transfer. So for a continuous structure, what is governing is What is governing is this. So what shall we do? We can write the questions. POA plus PE over Z1 minus MD or MA. So what is the minimum moment? It's MB. So we can say MB over Z1 so dead load moment is also not applicable. So RP over MP over Z1, MB over Z1. So it can go this way. Or it can go this way, Z1, it can go this way. So if it goes this way, we say it should be less than FT at working. RP over A plus PE over Z2 minus MB over Z2 can go this way, should be greater than FTW. Bottom fiber failing in compression. Then RP over A. This should be the top five, isn't it? This is the minimum moment. This is the minimum moment. So this has to be A, MA, MA, MA. This is the maximum moment. Maximum moment will cause RPO Z plus Z2, Z1. Maximum moment will cause compression at top fiber minus MB over Z1 should be greater than compression at top fiber, so it should be less than F compression at working. RP over A plus PE over Z2 minus MB over Z2. At the maximum moment, this can fail in compression. Minimum moment, it will fail in tension. So minimum moment, top fiber fails in tension. Minimum moment, bottom fiber can fail in compression. When it goes like this, minimum moment, bottom fiber can fail in compression. Maximum moment, bottom fiber will fail in compression. Top fiber will fail in tension. So that's it. Maximum moment, top fiber will fail in compression. Bottom fiber will fail in tension. So this is equation number 1, 2, 3, 4. Now you can see no transfer term comes, RP comes, so E should be greater than minus Z1 over A plus MA plus FTW Z1 over RP. E should be greater than minus Z2 over A plus MA plus FCW Z1 Z2 over RP. E should be less than minus Z1 over A plus MB plus FCW Z1 over RP. So these are all RP. E should be less than minus Z2 over A plus MB plus FTW Z2 for this is number 7, 8. So here you can see this is the Magnell diagram, Z1 over minus Z1 over A minus Z2 over A, and you get two equations. What are the conditions for those equations? For Z1 over A, Z1 over A should be greater than this. So this is equation number 5. This equation number 6. This equation number 6. E should be Z1 over A should be this number 7. This equation number 8. So what can you say? Gradient 6 should be greater than gradient of 8. What is the gradient of 6? Gradient of 6 is MA plus FCW Z2, and 6 should be greater than 8. MB should be greater than MB plus FTW Z2 over Z2. From this one, we can say Z2 should be greater than MB minus MA over FCW minus FTW. Similarly, you can say gradient of 5 should be greater than gradient of 7. See, gradient of 5 should be greater than gradient of 7. So gradient of 5 is MA FTW Z1 should be greater than MA plus FCW, MB plus FCW, Z1. From this, you get MA plus FTW Z1 should be greater than MB plus FCW Z2 Z1. From this one, you get Z1 shall be greater than MB minus MA divided by FTW minus FCW. These are negative quantity, these are again positive quantity, so you get the same thing, right? So you get a negative answer, minus answer. Here you get FT, this is addition, because FTW is negative, you get a positive quantity, here you get it. So you get the same answer for Z1 and Z2. So what is the meaning of this? The Z1 and Z2 will depend on the range, moment range, not on the moment. In a continuous structure, what is MB minus MA? This is MB, this is MA. It is the range of moment. And MD has nothing to do with it. M trans has nothing to do with it. But in the case of symmetry support case, this MD, ML, and MD at transfer is something like that. MD at transfer MD cos something. So the range depends on MD as well as ML. But here, it purely depends on the range of the live load moment. Purely depends on the range of the. So we have a great opportunity for optimizing the continuous structures. So prestress concrete is very good for continuous structures, provided you can construct it. But constructing prestress concrete continuous structures is not that easy. Why? You need to construct the structures continuous. So you have the abutment here, the piers here, piers here, piers here, abutment. So you have to have truss here, truss here, truss here. Construct it continuous. Apply the tenders like that. Prestress it. Not easy. Not easy. So that's why people have gone for this construction. Precast this, and using the topping, make it continuous. So we call this precast continuous construction. We call it pure continuous. There's nothing precast is pure continuous because this is precast construction. So all our expressways are this construction. Only port access is coming closer to this. That is coming closer to this. Port access road is coming closer to this. Closer, but not exactly. But all in Sri Lanka, all our construction has been like this, except I think Malampitiya Bridge and also Japanese Friendship. As well as right. So these are the two bridges in Sri Lanka which are truly pure continuous. All the other bridges are actually precast continuous construction. And Urugudawatta flyover is simply support. But we did a trick. What we did was we made the slab continuous and cut a groove. We have doubles there, and we filled up the groove with polysulfide. And then we put a geotextile on top of that, and then did the carpeting. So because of that, you don't see any join there, but it's not a continuous structure. It's a precast simply supported construction. There's a trick done. The trick, you don't see the expansion joints or contraction joints. You feel that it's a continuous construction. And our feeling is actually for Sri Lanka, there's no need to have expansion joints in bridges. You can have them simply supported or continuous, and there's no need to have expansion joints or contraction joints because our bridges our temperature variations are very small. Our temperature variations are very small. There's no need to have expansion joints or contraction joints. For concrete bridges, not for steel. Steel bridges must have expansion and contraction joints. Is that clear? Jayakodi, Giriagama, Disanayaka, Amarasena, Subasingha,
Yes, clear, sir.
right? So I have just covered the aspects. So I did not start with continuous bridges directly because that can cause confusion. So I showed the basic axial pre-stress, then I showed how to deal with simply supported, then continuous, not continuous, then simply supported, and then composite construction. Then I talked a little bit about loading that you have to master. I did not talk anything about analysis. Next time I'll talk about analysis for continuous beams. And then I talked about continuous beams and showed that continuous beams are based on N log 4 dead load, and there will be an N log 4 live loads, and what is governing will be the N log 4 N log 4 live loads plus dead loads, everything. But what is governing will be the die load range, not the other things. So that way you can see that the design of continuous beams differ a lot. And the biggest problem with continuous beams is what we call the reactant moments or secondary moments that we'll discuss next time. Okay? Is that clear?
Yes, sir.
Okay. With that, I'll end the lecture today. So I'll put the recording on mode.